And we're going to be talking about correlation and regression. Now, there's a lot more in the textbook on correlation and regression than what I'm going to cover either in this lecture and certainly in the homework and on the exams. I go into much more detail of correlation and regression in the second statistics class. That's after this one. But I want you to have a basic understanding of what correlation and regression are. So the first thing, a correlation exists between two variables when one of them is related to the other in some way. To find correlation, one thing you might do is graph the bivariate data where you have each value has two measurements, and one that we call the X measurement, one we call the Y measurement, and see if it looks like there's a pattern to the graph. With Minitab, it's easy to do a scatter plot. Go to Graph, Scatter Plot, with options of Simple, and enter in the X values and the Y values into the X variable, into the Y variable, and you'll take and then click OK. Minitab will give you a scatter plot. And you can see, does it look like the data, there's some kind of pattern? The most common pattern we're looking for is a linear pattern, or a data that approximates a linear set or a line. But there's also other relationships. There's parabolic relationships where the data takes on the shape of a parabola. Remember, that looks like a U up or a U upside down. Logarithmic, exponential. There's many types of relationships that we might be looking for, and a scatter plot would show us any of those relationships. If we're especially looking for a linear correlation pattern, and remember that the linear correlation association, or a linear association between these two variables, is the most common kind. Now, if we're dealing with quantitative data, which in this class we will be, in the second more advanced statistics class, we do look at other types of associations and correlations besides just two quantitative values. But for this class, we're going to be looking at just two quantitative variables. Then we're going to be looking for the Pearson product moment correlation coefficient. And it's also often just abbreviated linear correlation coefficient. It is denoted by a lowercase r. If we're looking at the population correlation, it is, which we're not so much in this class, maybe in the advanced class, yes, but not in this class. But if you were looking at the population, it's denoted by the lowercase r in Greek, which is called rho, and it kind of looks like a P. The Pearson product moment correlation coefficient measures the strength and the direction of the linear association between these paired X and Y quantitative values. It estimates rho. Remember, I told you rho kind of looks like a P, but it really is the lowercase r in Greek, the population parameter. Yes or no? The Pearson coefficient measures the strength of an association between an X and Y quantitative values in the sample. Think about it for a minute, but be careful. This has got a little bit of a trick to it. The answer is no, because Pearson doesn't measure an association, it measures just a linear association. So the Pearson coefficient may say that you have no linear association. That does not mean you have no association. There could be a very strong parabolic relationship, or there could be a very strong exponential relationship. It's just not a linear relationship. So interpreting R is always between -1 and 1 inclusive. If R equals -1, that means there is a perfect negative linear association, which means that the dots from left to right go down. And if R is equal to 1, then we have a perfect positive linear association, which means the dots lie perfectly on a line, and the line from left to right goes up. If R is equal to 0, that means there is no linear association. If it's close to 0, then we would conclude there's no significant linear correlation. Remember, it doesn't say there's no significant relationship, just not a linear relationship. And if R is close to 1 or -1, then the closer it gets to 1 and -1, the stronger the linear relationship gets. So remember when I said R represents the strength and the direction. So as the closer R is to 1 and -1 determines the strength of the linear relationship. If R is positive, that means the association, the linear association is positive, which means as our X values increase, our Y values are also increasing. And if R is negative value, then we say there is a negative association, linear association, and that means that as X increases, Y is decreasing. And how close is close? Okay, so usually we say anything between like 0.3 and -0.3 would be weak. But these are just guidelines, right? Between 0.3 and 0.5, we say moderate or a modest relationship, or between -0.3 and -0.5, we would say there is a modest linear relationship. Between 0.5 and 0.8, or -0.5 and -0.8, we say there's a moderate linear relationship. Once you get beyond 0.8 or get close to 0.8, between 0.8 and 1, or -0.8 and -1, we say there is a fairly strong linear relationship. So R determines the strength and the direction of the linear relationship. Using Minitab, we say go stat, basic stat, correlation. You input the values, and if the computed p-value is, it's going to give you an R value, it's called the correlation coefficient, and it's going to give you a p-value. If for the R, or the correlation coefficient, you're looking for values between 1 and -1, using the idea that the closer the value is to 0, the weaker the linear relationship. The closer the value is to 1 or -1, the stronger the linear relationship is. But the p-value tells you not that there's a strong relationship, tells you whether there's a significant linear relationship. And a lot of students get those two words confused. Significant does not mean strong. It just means it is linear enough to consider it linear. Strong means it's strongly linear. Significant does not necessarily mean strong. The value of R does not change if we convert to different scales. So if I'm measuring in inches or centimeters or meters or feet, the R stays the same. The value is R is not affected by which one we choose to be our independent variable and which one we choose to be our dependent variable. Whereas in the next section, when we look at regression analysis, that does matter. But if X is associated with Y, then Y is associated with X. If we interchange the X and Y, R does not change at all either. Now, R squared is actually take the value of R and square it. That is known as the proportion of the variation in Y that is explained by the linear association between X and Y. So let me give you an example that I often give to students. This comes from an actual study. Suppose I look at the association between the number of beers that someone drinks and their blood alcohol level. Well, it turns out there is a moderate linear relationship between the two. It's about a 0.49 positive linear relationship. So as the number of beers goes up, the R is 0.7. So and it's positive 0.7, which is a moderate, almost strong linear relationship, which means, since it's positive, it means that as the number of beers that we drink go up, our blood alcohol level is going up. That makes sense to all of you, right? Now, R squared means we take 0.7 and square it. If we take 0.7 and square it, we get 0.49. R squared says that only a little less than 50%, so only about 50% of your blood alcohol level, though, is explained by the number of beers you drank, right? So R squared is the proportion of the variation in Y that is explained by this linear association between the number of beers that you drink and your blood alcohol content. That means that there's about 50% of your blood alcohol content is associated with other things other than the number of beers you drink. It could be your metabolic rate, it could be your size, it could be what you ate, it could be how your body metabolizes sugar. Okay, there's other things. So R squared is how much of Y is being explained by the association between X and Y. If R equals 0, then X and Y have no correlation. I'm asking this question one more time because I'm trying to trick you again. I want to make sure you get the understanding that what? The answer to this is false, because no, it does not mean there's no correlation. It means that there is no linear correlation. So true or false, if X and Y have a strong linear correlation, then is it likely that X causes Y or Y causes X? Think about this for a minute. No, not at all. Linear relationship does not imply causation. For example, eating a salad is strongly related to lower BMIs. The more salad someone eats, the lower their BMI goes. So it's a negative relationship, and it's a very strong negative relationship. But that does not mean that eating salad is causing the lower BMI, because it's not. Because if it did, you could figure out a way to dehydrate a salad, put it into pill form, take 20 of those pills a day, which might be associated with eating 20 salads, and we would all have lower BMIs. We would have cured the world obesity, and we'd all be very rich, right? So eating the salad is strongly related to low BMIs, but the salad is not causing the lower BMI. Involving correlation. A lot of people say a strong correlation means causality. No, it does not at all. And if your data was averages, if you're looking at averages, like you're taking a bunch of data that is averaged and looking at these averages instead of the actual individual values, it often inflates the correlation coefficient. So it may seem that we have a stronger relationship than linear relationship than we really do. And there may be correlations other than linear correlations. I told you there's parabolic correlations, there's logarithmic correlations, exponential correlations, and those are just a handful of the ones that are possible. All right, so once you figured out that there is a significant, it does not have to be strong. Remember, the p-value being less than 0.05 says that you have a significant linear relationship. Not necessarily a strong linear relationship, but a significant linear relationship. So if you have a significant linear relationship, you do the correlation analysis, and the p-value for your correlation was less than 0.05, then you could move on to regression. Regression analysis says we take all this paired sample data, and we find the equation of a line that best models the relationship between those two variables. And remember, we've said that there's a significant linear relationship, or we would not have moved on to regression analysis, and thus finding the equation of a line makes sense. This line is often called the regression line. Sometimes it's called the line of best fit, or sometimes it's called the least squares line. And I get into the reason why that is in our more advanced class. I just want you to know that there's other names for it if you read it in another book. X is always going to be called the independent variable or the predictor variable, and Y is or the explanatory variable, and y is known as the dependent variable, also known as the response variable. So x is independent, also known as predictor, also known as explanatory. Y is the dependent variable or the response variable. Sample statistics B sub 0, B sub 1 are that if you looked at the equation of the line and think back to high school when you did y equals mx plus b, well, b1 is like the m, it's the slope, and b0 is like the y-intercept. It is the y-intercept. And they're used to estimate my population parameters of beta sub 0 and beta sub 1, respectively. So we have this equation of a line, y hat equals b sub 0 plus b1x. That's my sample. That line comes from my sample data, and it's used to estimate the y equals beta sub 0 plus beta 1x. Remember where b0 and beta 0 stand for the sample y-intercept and the population y-intercept, and b1 and beta 1 stand for the sample slope and the population slope. And if you remember from high school, the slope of a line is the rate of change of the y variable for each unit change in x. Only use regression if there is a significant linear correlation. Remember, we determine significance from the p-value. We determine strength from the r value. Without a significant linear correlation, so if the p-value turned out to be greater than 0.05, then our best predictor for the y value is the sample mean. If there is a significant linear correlation, we may substitute in a x value into the equation and get an estimated response variable value. But we must stay within the scope of the available sample data. If our model, if our linear equation came from a set of data that includes x values between 10 and 20, then we can't really plug in values for x being 5 or x being 50, right? It would only be a good predictor for values of x between 10 and 20. The marginal change, remember the marginal change is the slope. Remember this from high school. And the slope of the regression line represents the same thing that the slope of the line represented in high school. It represents the rate of change in the y when x is increased by 1 unit. Is really pretty easy. It's stat, regression, then another window opens up and you hit regression again, and then you hit fit regression model. Your response is your y values and your predictor are your x values. Then click OK. And it will give you the equation of best fit. It also gives you the r squared value, which is known as the coefficient of determination. If you want to see the graph, you can go to stat, regression, fitted line plot, and it will graph the data and include the line of best fit. And again, the response is the y values and the predictor is the x values. And you select linear model, because it does give you some other choices. Remember, there's other types of association besides just linear. The variation for a point, now this is what you do not, I'm going to cover this very fast. We're going to cover this in much greater detail in the next class, in the more advanced statistical analysis class. But for this class, I just want you to understand there is Minitab gives you a value for total variation. It also talks about the explained variation between the predicted value and the mean of the y values, or the actual y values and the mean of the y values. And the unexplained variation is the y value from the sample minus the predicted y value from the linear equation. Variation is found with this formula. It's y minus the y bar quantity squared. The explained variation is found by summing the y hat, which is the predicted value from the equation minus the mean squared. The unexplained value is the y from the sample minus the predicted value in the model. Note, total variation is the sum of the explained and the unexplained. You're going to see this. Minitab is going to give you this table that gives you all these values. We study this in great detail. In fact, great detail. We probably study it for like a month in the more advanced statistics class. But in this class, I just want you to know that this stuff exists. So variation for a sample, right? So we are given total variation is known as total SS on that table that Minitab gives you. The explained variation is known as the regression SS. The unexplained variation is known as the residual error SS. You see this all in this table in Minitab, but we're not going to do anything with it in this class. And then the total variation is the explained variation plus the unexplained variation. So it is the regression SS plus the error of SS. It's known as the coefficient of determination. It is equal to the explained variation over the total variation. This is its definition in terms of variation. But it is also what I told you a minute ago. It is the correlation coefficient R squared. Right? So we talked about that when I talked about the beer and the blood alcohol content, right? So you don't really need to figure it out by doing explained variation and total variation. In fact, Minitab just gives you the R squared. We have a standard error of the estimate, and you can use this formula, and it's the measure of the differences between the observed Y values and the predicted Y values. And note, Minitab calculates both for you, calculates the R squared and the S value for you, but we are going to use the R squared to some extent in this class, but not the S. Okay, so suppose I had this data and I put this into Minitab and I let one be, the interval be my Y and my duration to be my X. Duration into the X, I enter Y into the response. I go to stat, basic stat correlation. I enter in both columns, click OK, and I get R is equal to 0.926, which is fairly strong, and so I'm not surprised at all that my p-value is way less than 0.05. So there is a strong positive linear relationship. That's what R equal to 0.926 says. And it's significant. That's what the p equal to 0.001 says. Once I know that there is a significant linear relationship, I can move on to regression. So now I go to stat, regression, and fit regression model, enter in the Y values and the X values, click OK, and I get that interval after is equal to 34.77 plus 0.234 duration. The R squared is 85.67, and we usually denote R squared as a percent. So it means that about a little over 85% of the variation in the time intervals between the eruption is explained by the duration of the eruption, and about 14% remains unexplained. Looked at the table, we see the total variation, we see the explained variation, we see the unexplained variations. These are explained in much more detail later in another semester. So the graph of the regression line, we go to stat, regression, fitted line plot, enter in your Y, enter in your X, select linear, and click. And we see that we had a linear, it was very linear. If sometimes we're looking for a prediction. So to do prediction, we go to Minitab stat, regression, and then we go to prediction intervals. Right? Enter the desired confidence level and we prediction. So you go to stat, regression, predict. We enter the X value that we're trying to predict, let's say X is 180, into the box. Then we enter in a confidence level, the most common is 95%. If X was 180 is 76.90 minutes. That's the duration is 76.9 if the length of the eruption is 180 seconds. And we're 95% positive that the actual predicted value is somewhere between 63.47 and 90.33. The confidence intervals are used to predict the average/mean of all the Y values given for some X value. All right, we have multiple regression. Again, I just want you to understand the very basics of this because we're going to cover this in much more detail in the next class, the more advanced biostatistics or the more advanced statistics class. And it's the same idea, except instead of only having one predictor variable, we have multiple predictor variables. So let's open up, just to look at an example, let's open up the data from bears. Go to stat, regression, fit regression model. Let's enter in weight as the dependent variable. And as the independent variable, let's put in head length and length. So one is the length of the head and one other was the length of the bear. This data set bears can be found on the site www.triolastat.com, or I put it on the portal under bears. When we do that, we click OK, we get weight is equal to negative 425 plus 14.4 times the head length plus 7.18 times the bear length. This equation now can be used for predictions similar to the way we used for prediction with a single independent variable. So given a particular head length, given a particular length, we can predict the weight. Choosing the best multiple regression equation, you normally use common sense. So if you know something should be a good predictor, then you should consider it. But when you're looking at all these variables, you want to consider p-values to be low, and we want adjusted R-square values to be high. When we're dealing with a single independent variable, we look at the R-squared. If we're looking at multiple regression, multiple independent variables or multiple predictor variables, we look at the adjusted R-square. And we want them to be high. Remember, this again, I just want you to have a faint understanding of this is one of the main topics for the more advanced class. Chapter 10, which covered correlation and linear regression. Remember, all I want you to be able to do is find and interpret a correlation for strength, direction, and significance. And I want you to be able to find the regression equation for a single independent variable or for multiple independent variables and use it for prediction and find and predict the R-squared for simple linear regression and the adjusted R-squared for multiple linear regression, and be able to interpret it, what it means. All right, so now at this point, it's time for you to go do the assignments for Chapter 10 on the My Math Lab website. Then watch the lecture that I recorded to help you through Minitab Lab 10. Then download Lab 10, complete Lab 10, and upload it to the portal. Again, if you have any questions on the material or on the homework on the website or on the lab, please contact me and let me see if I can help you get back on track.